Welcome to this final module in this series of lectures on statistical quality assurance and statistical process improvement. We've been discussing the design and analysis of experiments, concentrating on 2 to the p studies and fractions of 2 to the p studies, that is, studies where p factors each have 2 levels and fractions of those. We're going to end this series with a nice example of a very small fraction. So we're going to talk about a 1/2000th fraction of a 2 to the p factorial, and give some perspective based on this example, on this whole set of material. We're going to begin and end with perspective that we should have gained on that last module with the Hansen and Best catalyst study, and that is that the larger is Q, that is, the smaller is the fraction that one is looking at of a full factorial, the more inevitable ambiguity there is going to be, and the more need for typically more need for follow-up study. Small fractions of large factorials are really only useful primarily as screening studies to pick out a few likely candidates for important variables, important factors in a study for a more detailed follow-up. The Hendricks chemical process study that we first saw in module 50, where we were introducing this set of material, it was one that had 15 factors labeled A, B, C, D, E, F, G, H, J, leaving out the I for reasons that we've got other uses for it. H, J, K, L, M, N, O, P, where the difference between P and Q, so there's P is 15, Q is going to be 11. That is, that example was one where only 2 to the 4th or 16 combinations were run, making it a 1 in 2048th fraction. That is literally 1/2048th of all possible combinations were used. The 11 generators employed are listed here. Just to review, this E equivalent to A, B, C, D statement says that signs for levels of factor E were set as products of signs for signs of products for A, B, C, and D all together. Signs for B, C, D were used to set levels of factor F, and so on. That led to 16 combinations and ultimately these data. Here are the data that were collected in that Hendricks study. They are listed in Yates standard order as regards factors A, B, C, and D. Okay, 4 factors, each at 2 levels, 16 combinations. If I look at this first row here, there is no A, B, C, or D in that name. In this second row, there is only an A, only a B, only an AB, only a C, an AC, a BC, an ABC, a D, an AD, a BD, an ABD, a CD, an ACD, a BCD, and an ABCD. That's Yates standard order for factors A, B, C, and D. If one does the 4-cycle Yates algorithm and gets estimated sums of effects from the Yates algorithm, one can try to do some kind of analysis to understand what these data are saying. It's not, I should say that here it's not going to make any sense to try to write out the whole defining relation. The generators are here, but a defining relation is going to say that the grand mean is literally indistinguishable from 2047 other things, and we'd still be writing here a couple of hours from now if I started listing everything that was aliased with the grand mean and so on. About all one can do here is to say, well, let's go back to the set of generators and suppose that all there is in this system are main effects, and see what we could find out or see what we would be pointed at under that very, very simple and perhaps naive and perhaps very wrong assumption that all that matters are main effects in this cold crack resistance study. The 16 observations, as I say, are listed in Yates order. Here again, if we run through 4 cycles, we do division by 16, which is 2 to the 4th, which is 2 to the 15 minus 11. Here are the estimates of sums of effects that come from that Yates algorithm. Now, by far the biggest things in this list are those 2 numbers. We don't have any replication, so the best we can do is to do normal plotting of the last 15 of those, and here is what we get from normal plotting. There are the 2 largest values in that list of estimates. If there were no factors if there were only 4 factors, on this line would sit the B main effect. But there are literally 2047 other things that could be written there, so we have to remember that. If there were only factors A, B, C, and D, this 106 would stand for the BCD 3-factor interaction, but there are 15 factors, so that 1.06 stands for BCD 3-factor interaction plus 2047 other things, one of which is the F main effect, and we know that because that's how we made up levels of factor F in the setting of the experimental combinations. That is, one of the generators is that F is aliased with, is indistinguishable from the BCD 3-factor interaction. So we could look at that and say, well, a very, very, very tentative interpretation is that what's important here is factor B and factor F. That if one assumes that what's important to any one of those sums of 2048 effects is really only the main effect, then it's B and F that matter. And in fact, if one wants large cold crack resistance, since these estimates are positive here, one wants the high level of B and the high level of F. It's interesting that if nothing else, as one looks back on this list of Y's here and looks for the cases where B and F are both present, it's there, and there. That is, the combinations that have both B and F at their high level are in fact the ones that have the 4 biggest Y's in that whole list. So if nothing else, we at least get pointed to the in retrospect quite obvious recognition that it's the combination of the data set with high B and high F that have the largest Y's. This is an example of, it's an extreme example of 2 to the P minus Q fractional factorial analysis, but it's a pretty nice one. It's one that illustrates both what is possible and the very limited, very tentative kinds of conclusions that one should be willing to draw based on such studies. Thank you for your attendance, your interest in this video series. We hope that it's been helpful.